Radioactivity is a phenomenon which is exhibited by elements with unstable nuclei. It was accidentally discovered by Henry Becquerel in 1896. While studying the phenomena of fluorescence and phosphorescence, Becquerel came across a mineral which shone in bright sunlight. But when the weather became cloudy, its fluorescence ceased. As the weather remained cloudy, he wrapped the mineral sample in black paper, put the contents in a closed desk, and forgot about it. Incidentally, the mineral happened to be placed over a Maltese cross, which was kept over a light-proof box of unexposed photographic film. Some days later, when Becquerel took the mineral out, he noticed that the photographic film appeared fogged. Becquerel reasoned that the material emitted fluorescence even in absence of sunlight. When the photographic film was developed, Becquerel found that the film was fogged with an image of the Maltese cross. This is how the photographic film looked after it was developed. Becquerel assumed that the fogging of the film was due to some rays emitted from the mineral compound, which could penetrate through the black paper and the silver cross and expose onto the photographic film. On further studies, it was found that the mineral Becquerel used in his experiment contained uranium salts, and that uranium emitted radiation constantly without any excitation or charge by an external source. Later studies and experiments based on these observations conclusively proved that this was a nuclear phenomenon known as radioactivity exhibited by some elements having unstable nuclei. Unstable nuclei can attain stability by emitting particles. A nuclear phenomenon in which an unstable nucleus undergoes decay is called radioactive decay. In nature, a radioactive nucleus can decay by three modes, namely the alpha decay, the beta decay, and the gamma decay. In alpha decay, a radioactive nucleus emits a helium nucleus, which is referred to as an alpha particle. In beta decay, a radioactive nucleus emits either an electron or a positron. A positron is a positively charged particle with mass same as that of an electron and magnitude of charge also exactly same as that on an electron. If an unstable nucleus releases an electron along with an antineutrino, it undergoes a beta minus decay. If it releases a positron along with a neutrino, it undergoes a beta plus decay. In gamma decay, the radioactive nucleus emits high-energy photon. A detailed study of alpha decay, beta decay, and gamma decay will be taken up later. Let us first derive a relation for the rate of radioactive decay. For this, let us consider a sample of a radioactive element containing n number of radioactive atoms at time t. The number of nuclei, Dn, which will decay, will be proportional to n, since the more the n value, more will decay in the time interval dt. The number of nuclei that will decay will also be proportional to the time interval dt. If we take a longer dt into consideration, then more nuclei will decay in this longer interval dt, since longer the interval, greater the chance of decaying. Thus, dn will be proportional to n dt. Or we can say dn will be equal to minus lambda n dt. Here, lambda is a constant of proportionality and is called the decay constant or disintegration constant. Negative sign shows decay of nuclei. This implies that dn by dt is equal to minus lambda n. Let this be equation 1. This can also be written as dn by n is equal to minus lambda dt. Let this be equation 2. Integrating equation 2, we get integral dn by n in the limits n naught to n is equal to minus lambda integral dt in the limits t naught to t. Here, n naught is the initial number of nuclei at time t naught, and n is the number of nuclei at a later time t. Evaluating the integral, we get log n to the base e minus log n naught to the base e is equal to minus lambda t minus t naught. If we take the initial time t naught as 0, we get log n by n naught to the base e is equal to minus lambda t. This can also be written as n is equal to n naught e to the power of minus lambda t. This equation is called the law of radioactive decay. Let this be equation 3. In general, we are interested in the number of nuclei decaying per unit time than the number of nuclei present in the sample. Number of nuclei decaying per unit time is known as the decay rate and is denoted by R. R is equal to minus dn by dt. Let this be equation 4. Decay rate R is also called the activity A of the sample. Substituting equation 3 in the equation 4, we get R is equal to minus d by dt of n naught into e power minus lambda t. Simplifying further, we get R is equal to lambda n naught e power minus lambda t. Let this be equation 5. Substituting equation 3 in equation 5, we get R is equal to lambda n. Now, at time t is equal to 0, let R be equal to R naught. Then, R naught can be written as R naught is equal to lambda into n naught. Substituting R naught in the place of lambda n naught in equation 5, we get R is equal to R naught e power minus lambda t. This is another form of the law of radioactive decay. Let this be equation 6. The SI unit for decay rate R is becquerel, denoted by BQ as shown. 1 becquerel is equal to 1 decay per second. Another unit of R is curie, denoted by Ci as shown. 1 curie is equal to 3.7 into 10 power 10 becquerel. The period of time taken by a substance undergoing decay to decrease by half is known as half-life period. It is the time interval for which both N and R are reduced to half of their initial values. Half-life period is denoted by T half. From equation 6, we have R is equal to R naught into e power minus lambda t. Substituting R equal to R naught by 2 and T equal to T half in equation 6 and solving, we get T half is equal to log 2 to the base e by lambda. Substituting the value of log 2, we get T half is equal to 0.693 by lambda. Let this be equation 7. Another measure of estimating the time for which a radioactive nuclei lasts is the mean life or average life, denoted by tau. It is the average time a substance exists in a specified form. It is the time interval in which N and R reduces to 1 by E of its original value. Let us now substitute R equal to R naught by E and T equal to tau in equation 6. We get R naught by E is equal to R naught into E power minus lambda tau. On simplifying, we get tau is equal to 1 by lambda. It shows that mean life tau is the reciprocal of the disintegration constant. Now, T half is equal to 0.693 tau. It is important to note that these relations for half-life and mean life are statistical in nature. They cannot predict the exact behavior of each and every nucleus in the radioactive sample considered. Rather, they only predict the total numbers. For example, consider a sample of 100 atoms of radioactive nuclide of half-life 20 hours. Since the half-life is 20 hours, we can say that 50 atoms of the radioactive sample would decay in 20 hours. But we cannot predict exactly which particular 50 atoms of the sample would decay. Experiments have proved that even though the sample contains all similar nuclei, under identical conditions, all of them may not decay simultaneously. Thus, it is impossible to predict when a particular nucleus will decay. However, prediction can be made about how many of these nuclei will decay in the small interval of time dt. Therefore, the equations developed for radioactive decay will work only when n is large. Previously, you have learnt about alpha, beta, and gamma emissions by relatively. From the curve showing the variation in average binding energy versus the mass number A, we have seen that elements with A ranging from 30 to 170, like iron, cobalt, etc., have relatively high binding energy per nucleon, EBN, and of nearly 8 MeV. The nuclei with average binding energy of approximately. From the same curve, we observe that the nuclei with mass number less than 30 and greater than 170 have binding energy per nucleon. This implies that when tightly bound nuclei transform into relatively less tightly bound nuclei, when such nuclear transformations occur, an enormous amount of nuclear energy is released, as in the case of nuclear fission or nuclear fusion, which you will learn in detail later. Let us now compare this energy to that which is released when we use conventional energy resources like coal, petroleum, etc. Conventional energy resources release energy through chemical reactions. For example, when 1 kilogram of coal is burnt, the amount of energy released is about 10 to the power 7 joule. But The nuclear energy released in the fission of 1 kilogram of uranium is about 10 to the power 14 joule, which is a million times greater than that released by a conventional source of energy. Therefore, the energy obtained from a nuclear source is considerably enormous compared to that obtained from an equivalent mass of conventional source of energy. At the same time, we have to remember that since a large amount of radiation is involved in such nuclear processes, they are extremely hazardous if not handled carefully. Let us now look at the nuclear processes which release such enormous amounts of nuclear energy. An Italian-American physicist, Enrico Fermi, found that when neutrons are bombarded onto various elements, new radioactive elements may be produced. For example, when cobalt-59 is bombarded with neutrons, it captures a neutron and transforms to cobalt-60, which is radioactive in nature. But when a uranium target is bombarded with a neutron, it splits into two almost equal fragments, accompanied by the release of a large amount of energy. This nuclear process is called nuclear fission. Let us look at an example of nuclear fission. When uranium-235 absorbs a neutron, it becomes unstable and undergoes nuclear fission. The fission products are barium-144, krypton-89, and 3 neutrons. It is also observed that in such type of fission, the products need not always be barium and krypton. The fission products of uranium-235 can also be antimony-133, niobium-99, and 4 neutrons, or xenon-140, strontium-94, and 2 neutrons. Thus, we see that nuclear fission involves the release of neutrons along with other products which may vary. We also see that the number of neutrons released also varies depending on the other products of fission being released. Let us now estimate the amount of nuclear energy or the value of Q being released during fission. Consider a nucleus of mass number A equal to 240 undergoing a nuclear fission. From the average binding energy versus mass number curve, we observe that for A equal to 240, the average binding energy is 7.6 MeV. Therefore, the total binding energy for this nuclide is 240 into 7.6, which is equal to 1824 MeV. Let us now assume that this nucleus undergoes nuclear fission and forms into 2 fragments with atomic mass number A equal to 120 each. From the graph, we find that for nuclei with A equal to 120, average binding energy is about 8.5 MeV. So, the total binding energy for the product nuclides is equal to 2 into 120 into 8.5, that is 2040 MeV for the 2 products put together. This shows that when a single nucleus of mass number 240 splits into 2 nuclei, the gain in binding energy is 2040 minus 1824, which is equal to 216 MeV. This energy is extremely large and is about 1 million times larger than the conventional energy sources like wood, coal, petroleum, etc. The enormous amount of energy which is the disintegration energy of the fission process initially appears as the kinetic energy of the fission products and the neutrons, and finally is transferred as heat into the surrounding matter. Thus, a nuclear fission process generates an enormous amount of heat energy. It is also observed that nuclear fission products are highly rich in neutrons and are unstable and radioactive. They emit beta particles in succession until they reach a stable end product. Put to proper use, this nuclear energy can be used to generate electricity in a nuclear power plant. On the other hand, high levels of energy and radiation in an atomic bomb can be obtained by an uncontrolled nuclear fission, causing grave damage to nature and mankind. Thus, the same fission reaction is the base for the useful nuclear reactor as well as the destructive atomic bombs. It depends on us how we use it. We know that when a uranium-235 nucleus absorbs a neutron, it undergoes fission and in the process releases neutrons. Nuclear fission of a heavy nucleus like uranium-235 yields enormous amount of energy. Also, 3 neutrons are released along with the fission products. In fact, an average of 2.5 neutrons are released in the fission of a uranium nucleus. We know that along with the fission products, say barium-144 and krypton-89, 3 neutrons are released during its fission. However, if these neutrons are absorbed by 3 other uranium nuclei, it can cause fission in them. Each uranium nucleus thus undergoes fission. Their fission results in the release of a total of 9 neutrons, which can cause further fission in 9 other uranium nuclei. In this manner, a chain of uranium fission reactions take place in a very short interval of time, thereby releasing an enormous amount of energy. This is called a chain reaction. It was first suggested by Enrico Fermi. A chain reaction is one in which the fission of a uranium nucleus, once initiated with the absorption of external neutrons, occurs rapidly without the aid of external neutrons. If a chain reaction is not controlled, it can be highly hazardous as it releases an enormous amount of energy that can cause harm to human beings and the environment to a large extent. The explosion of an atom bomb is an example of a chain reaction. It explodes due to the uncontrolled chain reaction of fissionable materials. If a chain reaction is controlled, we can harness an enormous amount of energy it releases for peaceful purposes such as generate electricity in a nuclear reactor. A nuclear reactor is a device in which a steadily controlled fission reaction takes place. Let us now study about the design and working of a nuclear reactor with uranium as the fissionable material. Uranium is taken in the form of cylindrical rods. These rods are arranged in a regular pattern within the active reactor core. The volume of the core is filled with a light nuclei material like either water, heavy water or graphite, which are called moderators. The neutrons released during the fission of uranium-235 have kinetic energies of approximately 2 million electron volt and are called fast neutrons. These fast neutrons escape from the uranium and enter the moderator. It is observed that the probability of uranium-235 undergoing fission is high when it absorbs neutrons with energies of approximately 0.04 electron volt that are typically called the slow neutrons. The probability of absorption of fast neutrons by uranium-235 is very low, and hence it does not help in the fission of uranium-235. The fast neutrons can be slowed down, that is, converted into slow neutrons by means of elastic scattering with light nuclei to sustain the fission reaction of other uranium nuclei. These light nuclei material called the moderator, which provided along with the fissionable material, slow down the neutrons released during fission and therefore help to increase the probability of fission of uranium-235 nuclei. Thus, the function of a moderator is to slow down the neutrons released during fission so that they can be absorbed by further uranium nuclei. In a pressurized water reactor, water is used as a moderator as well as a coolant to absorb the enormous amount of energy released in the reactor. The geometry of the core is such that out of an average of 2.5 neutrons released per fission, 1 neutron triggers the next fission reaction and the remaining ones are lost without causing further fission. That is, they are absorbed by the control rods. Control rods are used to control the rate of the fission reaction. Control rods are made of materials like cadmium. Cadmium is a very good neutron absorber, and it can be inserted into the moderator at a certain depth. Thus, the fission reaction can be sustained at a constant rate. Let us now define a quantity called the multiplication factor, K, for a reactor, which is a measure of the growth rate of the neutrons in the reactor. Multiplication factor K is defined as the ratio of the number of fissions produced by a specific generation of neutrons to the number of fissions produced by the previous neutron generation. As previously mentioned, out of an average of 2.5 neutrons produced, fission is always caused by 1 neutron only, and the value of K is equal to 1. This state is called the critical state of the reactor, wherein the reaction runs at a constant rate. If the cadmium rods maintaining the critical state are now drawn out of the reactor, then more number of neutrons will be available for further fission and the multiplication factor K becomes greater than 1. Thus, the fission rate increases rapidly and leads to an explosion. Again, consider the case when the reactor is just critical. If the cadmium rods are now pushed further into the moderator, they absorb more neutrons than earlier. The number of neutrons available for further fission becomes less. This reduces the multiplication factor K to less than 1. In such a case, the rate of fission decreases and the reactor shuts off. Thus, the control rods regulate the fission rate. In addition to the control rods, additional rods called the safety rods are provided in the reactor. Whenever required, these rods can be inserted into the reactor and can rapidly bring down the value of the multiplication factor K to less than 1. In the reactor core, a lot of energy in the form of heat is released, which can be utilized for the generation of electricity. Water at high pressure or molten sodium is passed through the reactor core to withdraw the heat produced in the core. The material that is used to extract the heat out of the core of a nuclear reactor is called the coolant. Nuclear fission and nuclear fusion are two nuclear processes that release enormous amounts of energy. You have already learned about nuclear fission. It is a process in which a heavier nucleus splits into two lighter nuclei with the release of a large amount of energy. Now, you will study about nuclear fusion. In the nuclear fusion process, two lighter nuclei combine to form a heavier nucleus, releasing a large amount of energy. For example, when two hydrogen nuclei, that is, protons, fuse together, a larger nucleus of deuterium is formed. In this process, a large amount of energy, approximately equal to 0.42 million electron volt, is released. Similarly, when two nuclei of deuterium fuse together to form a nucleus of helium, energy equal to 3.27 million electron volt is released in the process along with a neutron. Two nuclei of deuterium can also fuse together to form a nucleus of tritium, releasing an energy equal to 4.03 MeV along with a proton. In all these nuclear fusion processes, we see that two nuclei combine to form a heavier nucleus. We know that the nuclei are positively charged, and as such, the nuclear fusion process occurs only when the nuclei overcome the Coulomb's repulsive force between them and come close enough to be within the range of the attractive nuclear forces between them. The Coulomb's repulsive force is referred to as the Coulomb barrier, and the height of this barrier depends on the charges and also on the radii of the two fusing nuclei. If two protons, that is, two hydrogen nuclei, should fuse together, the barrier height is about 400 kilo-electron volt. This is a very huge amount of energy. To overcome the Coulomb barrier, the required energy is obtained thermally, that is, by raising the temperature of the proton gas. Let the temperature of the protons be raised to T to obtain energy of 400 kilo-electron volt. We know that the energy gained must be equal to 3 by 2 kT, where K is the Boltzmann's constant. Substituting the value of the Boltzmann constant and simplifying, we get temperature T equal to 3 into 10 power 9 Kelvin. Therefore, the temperature of the protons has to be raised to this value, so as to enable them to overcome the Coulomb barrier by thermal motion alone. This process is called thermonuclear fusion. Let us now consider the Sun's core, which is at temperature of about 1.5 into 10 power 7 Kelvin. But it is observed that protons fuse together in the Sun, even though the temperature is 100 times lesser than what is required for the protons to fuse. The reason for this puzzle lies in the fact that 3 by 2 kT represents the average kinetic energy of the molecules. But then, there are some nuclei which have kinetic energy more than the average values, and such nuclei overcome the Coulomb barrier. Therefore, we see that the Sun's core has extreme conditions of high temperature and high pressure to enable the nuclei to fuse together. Such thermonuclear fusion reactions occur in the Sun and other stars and form the source of the enormous amount of energy of the stars. We know the Sun has been a source of energy for us, over the past 5 × 10⁹ years, and estimates show that this can continue for the next 5 billion years. Obviously, the fusion reaction taking place in a repetitive cycle forms the source for such continuous energy generation. In the nuclear fusion process taking place in the Sun, hydrogen nuclei fuse together to form the heavier helium nucleus and, in the process, release enormous amount of energy. This is a multi-step process and is called the proton-proton cycle of nuclear reactions. In the first step of the proton-proton cycle, 2 hydrogen nuclei fuse together to form a deuteron releasing a positron and a neutrino along with energy. The deuteron formed in the first step fuses with another hydrogen nucleus to form a lighter helium-3 nucleus releasing gamma rays. In the last step of the process, the helium-3 nucleus combines with another helium-3 nucleus to form a stable helium-4 nucleus along with 2 hydrogen nuclei releasing energy in the process. For the last step to occur, the processes represented by equations 1, 2 must occur twice. The net effect of the above multiple step process is that 4 hydrogen nuclei fuse together to form a helium nucleus releasing 2 positrons and gamma particles along with energy equal to 26.7 million electron volt. This process is estimated to run in the Sun's core for about 5 billion more years, by which it would mostly contain helium nuclei. Then, the Sun's core will begin to cool down and the Sun will collapse under its own gravity. In this phase, the Sun will be called the red giant. If the temperature of the Sun rises again to 10⁸ Kelvin, then helium nuclei can fuse to form carbon. As the star evolves further and becomes hotter and hotter, other elements with more number of protons can be formed. But we must note that the elements more massive than those which are near the peaks of the binding energy curve cannot be formed by further fusion. The first thermonuclear fusion reaction occurred on the Earth by the explosion of a nuclear fusion device, and energy equal to about 2.6 × 10⁻29 million electron volt was produced in the process. It occurred at Nuclei Atoll, a part of Marshall Islands in North Pacific. However, we must note that a sustained and controllable source of nuclear fusion power is difficult to achieve on the Earth due to the inherent difficulties involved, like conditions existing in stars.